Good morning, students. This is Addagatla Nagaraju, lecturer in Electrical and Electronics Engineering, Government Polytechnic, Station Kanpur. Today, we are going to learn BEE 5th semester's AC Motors subject. In AC Motors subject, 3-phase induction motor chapter we are covering. In 3-phase induction motor, speed control of induction motor by injecting voltage in rotor circuit by changing a rotor circuit resistance and by cascading method. These three methods we will see today. Okay, so from this topic we are completely covering 3-phase induction motors chapter today, and then from next class onwards we will start single-phase induction motors. Okay, so what we have discussed in last class. So in last class also we are discussing about speed control techniques. In that, speed control of induction motor by pole changing method, we have seen two different methods, different speeds we can obtain. Two types of methods, consequent pole method. Okay, so coming to this, today's object is on completion of this period, you will be able to know speed control of induction motor by injecting voltage in rotor circuit method, speed control of induction motor by changing a rotor circuit resistance, speed control of induction motor by cascading methods. So we will see injecting voltage in rotor circuit, changing a rotor circuit resistance, cascading. Okay, these three methods we will cover. So once we will recall what we have known in last classes, on which factors speed of the induction motor depends. N is equal ns into 1 minus s. So it depends on synchronous speed, it depends on speed. On which factor synchronous speed depends, on which factor speed depends, voltage depends. By changing the voltage, motor draws extra current that may result in excessive speed. And the synchronous speed 120 F by P. By changing the poles and frequency, we can change the synchronous speed. By changing the voltage, we can change the speed. What is the form of per speed of induction motor? NR is equal ns into 1 minus s. What happens if the voltage is induced in the rotor circuit? That may change the slip. What happens if slip decreases? Slip decreases, speed increases. What happens if the rotor circuit resistance is changing? Rotor circuit resistance is changes, the torque changes. The torque will change the speed. Okay. Speed of the induction motor N is equal to ns into 1/6, where synchronous speed ns is equal to 120 F by P. 120 F by P, where S is the slip. Rotor copper losses per rotor input. Hence, from the above expression, it can be concluded that speed of the induction motor can be changed by either changing its synchronous speed or by changing its slip. Speed control of induction motor by injecting voltage in rotor circuit. The speed of induction motor can be controlled by injecting a voltage of slip frequency into the rotor circuit. If the injected voltage in phase with the rotor, induced EMF is equivalent to decreasing the rotor resistance. Hence, slip decreases, speed increases. If injected voltage is increased, opposition to the rotor induced EMF is equivalent to increasing the rotor resistance. Hence, slip increases or speed decreases. A large and smooth variation of speed is possible by this method. However, it requires auxiliary machine capable of injecting the correct slip frequency voltage into the rotor circuit. Therefore, it is costlier and used with motors of very large rating. Nowadays, these motors are rarely used because of the bulky construction and prohibitive cost. But in this method, any speed within working range can be obtained. The method is applicable only to slip-ring induction motors in squirrel cage motors. The rotor circuit resistance can't be varied by increasing the rotor resistance. The slip increases and hence the speed decreases. So by inserting external resistance in the rotor circuit, slip increases and speed decreases. Since slip is equal to rotor copper loss by rotor input, however, addition of resistance in the rotor circuit increases the rotor copper losses, which reduces the efficiency. Therefore, this method should be used only when speed control is required for a short period. When external resistance is put in series with each phase of the rotor circuit, the rotor copper losses increases. Slip is equal to rotor copper losses by rotor input. If the rotor input remains constant, the increase in rotor resistance will increase the slip. Thus, The motor speed NR is equal to 1 minus S into NS will decrease. Thus, the speed below normal only can be had. The main disadvantage of this method is that with increasing rotor resistance, the rotor copper loss also increases, which proportional to the reduction in speed. Hence, this method is used where speed changes are needed for short period only. Also, this method gives poor speed regulation, that is, the variation of speed with of load becomes higher is shown in the figure. With inserting additional resistance, the starting torque is increased. Starting torque is increased and maximum torque obtained for a lesser speeds. These are the speed torque characteristics. When inserting a resistance in the rotor circuit, from figure 1, change of load from off load to full load, variation of speed is from N1 to N2 with R2 as the rotor resistance, variation of speed from N3 to N4 with R2 dash as the rotor resistance, which is much higher compared with R2 as rotor resistance. Okay, coming to the next method, on which factor speed of the induction motor depends. Slip and synchronous speed. Speed formula n is equal to 1 minus S into Ns. What is meant by cascading? By mechanically connecting one motor to the another motor. This is also called concatenation or and in operation of induction motors. In this method, two motors are required, at least one of which must have slip ring type called as main motor, while the second motor is called auxiliary motor, maybe either slip ring or cage motor. The two motors are mechanically coupled as shown in the figure so that both run at the same speed. The stator of main motor is connected to three-phase supply, while the auxiliary motor is fed from the rotor circuit of main motor. This is called as cascading of motors. This is, this is the main motor. The auxiliary motor and main motor are mechanically coupled. Mechanically coupled, and the supply to the auxiliary motor from the rotor of the main motor. The rotor of the main motor. If the torque produced by both acts in the same direction, cascading is called cumulative cascading. If torque produced are in opposite direction, cascading is called differential cascading. Let T1 is the number of poles of main motor, T2 number of poles of auxiliary motor, F supply frequency due to cascading. Four different synchronous speeds are possible. Main motor is connected to supply independently. So Ns is equal to 120 F by P1. Actually, the motor is connected to supply independently with main motor disconnected from the supply. So Ns is equal to 120 F by P2. In cascading combination, cumulative produces the effective number of poles P1 plus P2. Therefore, Ns is equal to 120 F by P1 plus P2. In differential cascading, the effective number of poles P1 minus P2. Therefore, Ns is equal to 120 by P1 minus P2. Proof of cascaded speed of the set 120 by P1 plus P2. Synchronous motor 1 is N1s is equal to 120 by P1. Let S1 has to be the skips of the motors 1 and 2. Now, the supply frequency of motor 2 is S1 into F. Therefore, synchronous speed of the motor 2 N2 S is equal to 120 S1 F by P2. Actual speed of motor 1 N1 is equal to N1S into 1 minus S1, that is equal to 120 by P1 into 1 minus S1. Actual speed of motor 2 N2 is equal to N2S into 1 minus S2, that is equal to 120 into S1 S by P2 into 1 minus S2. As the two motors are mechanically coupled, the two speeds must be same. As the two motors are mechanically coupled, two speeds must be same. Hence, 120 F by P1 into 1 minus S1 is equal to 120 S1 F by P2 into 1 minus S2, or 1 minus S1 by P1 is equal to S1 minus S1 into S2 by P2, but the terms S1 and S2 are very small and neglected. Hence, 1 minus S1 by P1 is equal to S1 minus S1 into S2 by P2. Small terms S1 and S2 are very small and neglected. Hence, 1 minus S1 by P1 is equal to S1 by P2. S1 P1 is equal to 1 minus S1 into P2. S1 P1 is equal to P2 minus S1 P2. S1 is equal to P2 by P1 plus P2. Hence, speed of the set and is equal to 120 F by P1 into 1 minus S1. 120 F by P1 into 1 minus S1. S1 means P2 by P1 plus P2. That is equal to 120 F by P1 plus P2. Therefore, associated speed of the set 120 F by P1 plus P2. The actual speed will be less than this by the slip factor. In general, it can be concluded that speed control of induction motor is much more difficult than the DC motor. We will be the derivation, we will see once again. This is the cascading condition. The torque produced by both act in the same direction. Cascading is called cumulative cascading. When the torque produced are in opposite direction, cascading is called the differential cascading. Let P1 is the number of poles of main motor. P2 number of poles of auxiliary motor. F supply frequency. Due to cascading, four different synchronous speeds are possible. Main motor is connected to supply independently, so MS is equal 120 F by P1. Auxiliary motor is connected to supply independently with main motor disconnected from the supply, so MS is equal 120 F by P2. In cascaded combination, cumulative produces the effective number of poles P1 plus P2. Therefore, MS is equal 120 F by P1 plus P2. In differential cascading, the effective number of poles are P1 minus P2. Therefore, NS is equal to 120 F by P1 minus P2. Proof of cascade speed of the set 120 F by P1 plus P2. Speed of motor 1 is NS1. N1S is equal to 120 F by P1. Let S1 and S2 be the slip of the motors 1 and 2. Now the supply frequency of motor 2 is equal to S1F. Therefore, synchronous speed of the motor 2 into S is equal to 120 S1F by P2. Actual speed of motor 1 N1 is equal to N1S into 1 minus S1. That is equal to 120 F by P1 into 1 minus S1. Actual speed of motor 2 N2 is equal to N2S into 1 minus S2. That is equal to 120 S1 F by P2 into 1 minus S2. As the two motors are mechanically coupled, the two speeds must be same. Hence, 120 F by P1 into 1 minus S1 is equal to 120 S1 F by P2 into 1 minus S2. Now, 1 minus S1 by P1 is equal to S1 minus S1 S2 by P2. But the term S1 and S2 very small head is neglected. One minus S1 by P1 is equal to S1 by P2. S1 P1 is equal to 1 minus S1 into P2. S1 P1 is equal to P2 minus S1 P2. S1 is equal to P2 by P1 plus P2. Hence, speed of the set N is equal to 120 F by P1 into 1 minus S1. 120 F by P1 into 1 minus P2 by P1 plus P2. Is equal to 120 F by P1 plus P2. Then from cascaded speed of the set 120 F by P1 plus P2. Actual speed will be less than this by slip factor. In general, it can be concluded that the speed control of induction motor is much more difficult than a DC generator. So, formula for speed of the induction motor and S into 1 minus S. Cascading, we already seen the cascading connection. Disadvantages. This method is rarely used due to the following disadvantages. It requires two motors, which makes the set expensive. Smooth speed control is not possible. Operation is complicated. Do you know what are the applications of induction motor? What are the applications of synchronous motor? Which self-starting and which motor is not self-starting? So, applications of induction motor. Induction motor is used in everywhere. This is also called the workhorse of industry. So, synchronous meter has two different applications: power factor increment and mechanical load. It has low speed applications. Induction motor is self-starting motor. Synchronous motor is not a self-starting motor. Coming to the applications of induction motor, the three-phase induction motor is most widely used in industry and workshops. The squirrel cage induction motor is generally built in small size up to few kilowatts. The bigger sizes wood rotor motors are preferred. An induction motor is a nearly constant speed motor, has hardly any competitor. Other type of motors are considered only when a variable speed drive is needed. Applications of three-phase induction motors of size varying from half a kilowatt to thousands of kilowatts are numerous. Induction motors are found everywhere from small workshop to large manufacturing industry. Therefore, it is possible to specify an appropriate motor for a given application. It is necessary to know the load characteristics. Load characteristics will include terms like horsepower requirement, starting torque, speed variation, duty cycle, environmental condition, etc. Applications of various types with respect to starting current of squirrel cage motor, wood motor are mentioned below. Squirrel cage motor, general purpose with normal torque and normal starting current. It has applications fans, blowers, centrifugal pumps, lines, shafting tubes, wells, floor mills, etc. High starting torque and low starting current, conveyors, compressors, crushers, reciprocating pumps, etc. High starting current and medium current and high slip used for high inertia loads such as shears, punches, presses, die stampings, etc. Rotor motor. These motors are used in situations where high starting torque and low starting current is required, such as conveyors, cars, compressors, pumps, etc. Squirrel cage motors. It has moderate working torque and a constant speed characteristics preferred for driving fans, blowers, water pumps, grinders, painting machines, welding machines, lathe machines, etc. Slip ring motors. It has having high starting torque preferred for lifts, hoists, elevators, cranes, compressors, etc. Comparison between synchronous motors and induction motors. Synchronous motor is a mirrored starting motor, but induction motor is a self-starting motor. So synchronous motor is not a self-starting motor. Additional we need additional devices to start the synchronous motor. That may be pole motor, that may be another induction motor. Okay, that may be induction generator, etc. Three-phase induction motor is a self-starting motor. So construction is complicated because synchronous motor rotor construction is somewhat difficult because it is a really excited motor. Okay, it has two supplies. Rotor also we need to provide DC supply. For that we need a commutator, slip ring and best sets. But construction of cage motor is very simple because it is a simple iron cage. Synchronous motor speed control is not possible because it is a constant speed motor. It runs with a constant speed, synchronous speed. But induction motor speed control is possible. Synchronous motor runs at constant speed, that is synchronous speed irrespective of load. Induction motor, it cannot run at synchronous speed. The synchronous, the speed decreases as the load increases. It is doubly excited machine and requires DC excitation for the rotor to create north and south poles. Coming to the induction motor, it is singly excited machine. It does not require any DC excitation. It can operate with a wide range of power factors, both lagging and leading. It always operates at a lagging power factor. So, overexcited synchronous motor acts as leading power factor. Underexcited synchronous motor acts as lagging power factor. But induction motor always lags, so it runs with a lagging power factor. Coming to the synchronous motor, it is used for supplying mechanical loads as well as power factor improvement. It has two types of applications. Coming to the induction motor, it is used for supplying mechanical loads only. Synchronous motor, its torque is less sensitive to changes in supply voltage. Induction motor torque is more sensitive to change in supply voltage. Synchronous motor hunting starts as load changes suddenly. Induction motor phenomenon of hunting is absent because it always hunts with a lesser synchronous speed. The synchronous motor due to overshooting hunting may cause speed. Synchronous motor is very much costlier and requires the maintenance because it has bed sets, different rotor construction. Coming to the induction motor, it is cheaper and almost maintenance free, particularly in case of cage motor. We have discussed so far speed control of induction motor by injecting voltage in the rotor circuit, speed control of induction motor by changing the rotor circuit resistance, speed control of induction motor by injecting voltage in rotor circuit method. And also we had discussed the applications of induction motors, comparison of synchronous and induction motors. Okay. Coming to the case, if injected voltage is in phase opposition to the rotor, induced EMF is equivalent to the dash rotor resistance. If injected voltage in phase opposition to the rotor induced EMF is equivalent to the dash rotor resistance. Option A increasing, option B decreasing, option C both A and B, option D none of them. So induced voltage, if you induce some voltage then slip decrease, speed increase. Slip decrease, speed increase. Okay. Then if you increase the resistance also, torque increase, that means current increase, that means slip. Okay, so by increasing the resistance or by decreasing the EMF, both will do the same, but by decreasing the voltage, slip decreases. Slip by decreasing the voltage, slip increases, speed decreases. Similarly, by increasing the resistance, slip decreasing, slipping as per Allah, slip increasing and speed decreasing. So increasing the voltage and decreasing the resistance is the same. Decreasing the voltage or increasing the resistance also same. Speed control of induction motor by changing rotor circuit resistance method is applicable only to dash types of induction motors. Option A, split ring. Option B, squirrel cage. Option C, both A and B. Option D, none of the A. Speed control of induction motor by changing rotor circuit resistance. So, the rotor circuit resistance we need to change. Then we have a open circuit rotor we need available and slip rings are available. Then slip ring induction motor is the only motor applicable. If slip increases, then speed. Slip increases, then speed decreases because the formula M is equal to ns into 1 minus s. 1 minus s. Slip increases, speed decreases. So coming to the summary, what we have discussed is applications of induction motors, comparison of synchronous and induction motors. So from these topics, this induction motor speed control is dash possible. Option B, not possible. Option C, don't know. Option D, none of the above. Induction motor speed control is possible but difficult. In synchronous motor, speed control is option A possible, option B not possible, option C don't know, option D none of this. The synchronous motor is a constant speed motor, its speed control is not possible. Hunting is possible in option A induction motor, option B synchronous motor, option C both A and B, option D none of these. So hunting is possible in synchronous motors only. In cascade control method, how many motors are required? Option A 1, option B 2, option B C, option D 4. Cascaded control method, how many motors are required? Cascading method, 2 motors are required. 2 motors are in cascaded control method. 2 motors are required, at least one of which must have gas type motor. Slip ring, option B induction motor, option A slip ring induction motor, option B spiral cage induction motor, option C both A and B, option D none of these. One should be a slip ring induction motor because from this slip rings we are giving supply to the next motor. Cascaded speed of the set 120 F by P1 plus P2, P1 minus P2, P1 plus P2 by P1 minus number cascading P1 plus P2. Speed is decreasing due to increasing in the poles. Coming to the frequently asked questions. List the various methods of speed control of induction motor. Explain how the speed of induction motor can be changed by injecting voltage in the rotor circuit method. Explain how the speed of induction motor can be changed by changing the rotor circuit resistance. Thank you.